Hi everyone, I'm Raja, and today I'm going to speak about evolvability for interdomain routing. This is joint work with my colleagues David Tran Lam and Aditya Akella from the University of Wisconsin and Peter Stenkesty from CMU. So many in the room might know that interdomain routing has not changed for many years. BGP, which is the current protocol for connecting every machine on the internet, is riddled with flaws and limitations. Examples include lack of security, lack of knobs for traffic engineering, and the fact that it indiscriminately chooses a single best path per router or domain. Owing to this, many critical fixes to BGP, value-added protocols that are meant to run in parallel with BGP, and replacement protocols that have been proposed in the research literature and in operator communities. But despite the existence of this rich landscape of protocol alternatives, almost none have been deployed or used broadly on the internet. BGP, flaws and all, has remained unchanged since the mid-1990s. We argue that a key reason for this lack of progress is that today's internet control plane, basically BGP, is very architecturally rigid and does not support evolution to new protocols. As such, even if there was some amazing new protocol that operators really, really wanted from this rich landscape, it would be very difficult for it to gain traction. So here's an example that shows how BGP does not support evolution to new protocols. What you see on the screen is a simple internet topology. Autonomous systems, or ASs, are shown in blue and white. Blue ones support an augmented version of BGP, called Wiser, that fixes BGP's broken support for traffic engineering by propagating an extra path cost metric with path advertisements. The costs are used as input to Wiser's best path selection process. The path selection process is otherwise identical to BGP. White ones here only support BGP. So just a quick refresher, path selection in BGP-like protocols happens in the control plane. ASs receive any number of path advertisements to destinations, pick a single best one per interdomain router or interdomain link, and disseminate only that one to its neighbors. So the blue AS on the right over there will receive two path advertisements for either side of the diamond, and will choose one of them and propagate only one of them to its other blue neighbor at the top of this topology. So ASs in the right Wiser island, that is, contiguous group of ASs that support the same protocol, in this case Wiser, select best paths using this path cost metric. The arrows show advertisements of the best paths in this region. The thickness of the arrows shows which of the two paths ASs in this region think is better. In this case, the top one, because it has a lowered path cost. But what happens when advertisements must be disseminated across ASs that support only BGP? For example, across this gulf of BGP ASs over here. Wiser can't be used anymore. This is because these BGP-only ASs do not understand Wiser's path cost metric and will not disseminate it to other ASs. BGP must be used instead from now on. BGP prefers shorter paths to longer ones. So the notion of which of the two paths is better switches as soon as the gulf is reached. As such, the source AS, which supports Wiser, will actually end up picking the shorter, lower quality path instead of the longer, higher quality one. So this limitation of not being able to use new protocols across gulfs makes it difficult to use new interdomain routing protocols quickly, reducing incentives for operators to support or deploy them. So this research is about understanding what small modifications need to be made to BGP to enable evolvability support. To do so, we analyzed recently proposed protocols to understand requirements these modifications must satisfy to enable evolvability to a wide range of protocols. Based on these requirements, we proposed two modifications to BGP that we think are sufficient to enable evolvability. The first is pass-through support on routers or within SDN controllers. This modification allows control information about unsupported protocols, for example, path costs, to be disseminated across gulfs of ASs that don't support those protocols. The second is integrated advertisements, which is a data structure that allows multiple protocols' control information to be encoded in a single BGP-like advertisement. So first, I'll talk about how we identify the requirements, and then I'll discuss the modifications for a bit. So here's the process we use to identify requirements for evolvability. First, we analyzed a range of protocols, around 12 or so far. Not all of them are shown here. We were looking for some way to group them so that common themes emerged about what evolvability support would mean for them. The insight we came to is that bitting them according to the deployment method, that is what data plane support is provided to facilitate a given protocol's use in an internet comprised of multiple interdomain routing protocols gave rise to these common themes. So kind of the high-level intuition here is that the control plane supports the data plane. So differences in data plane support needed will naturally give rise to differences in the control plane, and hence differences in control plane evolvability requirements. The specific data plane support that matters is routing consistency. That is, whether a given protocol's path choices must be enforced at every domain that supports the protocol, and or even at domains that do not support that protocol. We found that different deployment methods are naturally suited to different deployment goals, deployment methods. The first goal is introducing protocols that provide critical fixes to BGP by disseminating extra control information to improve path selection. Examples include WISER, RBGP, or SBGP. The second goal is introducing protocols that run in parallel with BGP and provide services it doesn't. For example, alternate paths or hierarchy OS. Examples include Miro and Arrow. The third goal is replacing BGP entirely with a fundamentally different protocol. Examples might include moving from BGP to Scion, which is path-based. It exposes multiple paths per interdomain link and allows sources to pick which one they want to use. Finally, we found that the deployment method, in combination with the goals each method is suited for, informs these control plane evolvability requirements. So first, I'd like to spend a few minutes discussing why routing consistency is important for some protocols, and then I'll discuss the different methods. So here's a slide that illustrates Miro and why lack of routing consistency is problematic for it. Miro is a protocol that provides alternate paths to those provided by BGP for select traffic. ASs that are green and white run both BGP and Miro, and ASs that are white support only BGP. There are two Miro islands, one on the right, which includes 3 ASs, and a singleton one on the left. There's also one BGP Gulf comprising 3 ASs. Recall the islands are contiguous ASs that run the same protocol. In this example, the source AS wants to avoid AS2 when routing to the destination. Unfortunately, the BGP path it must use, shown in black, includes this AS. So instead, wants to use an effective path enabled by Miro, shown in green. There are 2 problems with trying to send traffic via this path. First, across gulfs, packets addressed to destination will normally be forwarded using BGP's chosen path. So even if the source AS intends packets to be routed to the destination via M1, the effective path that will be used by packets will be an unwanted hybrid, in this case containing the source AS, the AS the source wants to avoid. Even if routing consistency were provided across gulfs, unwanted hybrid paths might still be used, because islands that support Miro and BGP cannot distinguish traffic meant to be routed from each other. This is because they use the same forwarding tables in this example and forward based on the same destination address. There's simply no way to distinguish packets meant for Miro from packets meant for BGP. So in this case, if a router within M1 forwards traffic using BGP's forwarding decisions, a different hybrid path would be used, which might include AS2. So I'm not going to go into much detail about how routing consistency can be provided, but at a high level, encapsulation and tunneling can be used across gulfs, and within islands, separate address spaces can be assigned to different protocols. So on this slide, I'm going to show the 3 deployment methods we came up with, show how they differ, and identify their evolvability requirements. The first is hybrid routing. This method provides no routing consistency, both across gulfs and within islands. As such, the routing paths that will be used are hybrids, composed of multiple protocols forwarding choices. It is best used for protocols that update BGP with critical fixes, because these protocols can fundamentally use each other's paths. Examples include WISER and SBGP. These critical fixes that wish to avoid hybrid paths, such as SBGP, can do so during path selection. There are 2 evolvability requirements for this deployment method. First is allowing new protocols extra control information to be disseminated across gulfs. This will enable the creation of fully hybrid paths where the new protocol is used where it's supported and BGP is used where it isn't. The second is allowing BGP to be gradually deprecated in favor of the new protocol. The second requirement prevents overlay-based approaches from being used because they would always have to rely on the underlying protocol, which would probably be BGP. So here's the WISER example from earlier in the talk. It can be deployed using hybrid routing because BGP and WISER can essentially use each other's paths. Recall that the key problem was that the source AS, which supports WISR, could not use it because path costs were not disseminated across these gulfs. Allowing new protocols control information to carry through these BGP gulfs would fix this problem. Also, since WISR is a critical fix, the intention would be for all ASs on the internet to eventually use this, not BGP. The second deployment model is consistent routing. The deployment method provides routing consistency both across islands, so within islands and across gulfs. It is best used to introduce custom protocols within islands that will use in parallel with BGP and provide services that BGP doesn't. Routing consistency is needed to keep traffic intended for the new protocol from being forwarded using BGP and vice versa. Example protocols that could be deployed using this method include Miro and Arrow, which provide alternate paths or higher QoS to select customers for payment. This model can also be used to introduce new paradigm protocols for routing select traffic. One example is Scion, which is path-based, and Pathlets, which is path fragment-based. The key evolvability requirement for this deployment method is off-BGP path discovery of ASs or islands running the new protocol. Here's our Miro example to show why off-path discovery is important. Note that in this example, without non-BGP mechanisms, the source AS cannot ever discover that M1, M2, or the destination support Miro. It must know that at least M1 supports Miro to be able to obtain an alternate path that avoids AS2. Lack of discoverability here occurs because the BGP best path does not include M1. Even if the best path did go through M1, information identifying that it supports Miro would not be disseminated across the BGP gulf. The final model is exclusive routing. I'm not going to discuss this model during this talk, but please see the paper for details. So next, I'd like to spend a few minutes quickly describing our proposed modifications to BGP that satisfy the requirements that I just identified. Once again, these are pass-through support and integrated advertisements. I'm going to focus on how they enable evolvability for hybrid routing, though I'll sprinkle bits and pieces of how they're useful for protocols deployed using the other methods as well. So integrated advertisements and pass-throughs replace BGP's regular advertisements and advertisement processing. They can be implemented in routers, in ASs that use distributed control, or in SDN applications in ASs that use centralized control. Both integrated advertisements and pass-throughs are limited to evolvability for path vector style protocols, so using them to move to something that's, say, link state based would be a bit difficult. Pass-throughs enable evolvability for hybrid routing by allowing new protocols control information to be propagated across gulfs. Examples of such control information including WISR's path costs or, say, SBGP's route attestations. Integrated advertisements allow pass-throughs to be used because they encode multiple protocols control information in a single advertisement. They enable gradual deprecation of BGP because new protocols control information is encoded side by side with BGP. ASs can start using a new protocol and stop using BGP as soon as they support the new protocol. So I'm not going to, okay. Right. On this slide, I'm going to show how pass-throughs work. The ASs on the bottom form a simple topology. Blue ones support a critical fix, maybe a WISR, and white ones support only BGP. So let's have a look at a router or SDN application within the BGP AS. Let's assume it's a router. This router contains a pass-through module. Please see the paper for its proposed architecture. It also contains one or more decision modules corresponding to the protocol supported. In this case, there is only one, corresponding to BGP. Decision modules contain protocol-specific logic and data structures, such as the best path selection algorithm. When a new integrated advertisement arrives, the pass-through module extracts control information for the protocol the router supports and sends it to the appropriate decision module. In this case, BGP is one. The decision module returns a new best path choice and updated control information. Let's assume that it picks the path in the incoming advertisement. The pass-through module installs the best path choice in the data plane and creates a new integrated advertisement with the updated control information. In doing so, it simply copies over the extra control information for unsupported protocols contained in an incoming advertisement for the selected best path. This allows unsupported control information to cross gulfs. Some goals we think a data structure for integrated advertisements should satisfy are as follows. First, it should state all the protocols that can be used in a routing path being created. Second, they should be expressive enough to encode control information for a wide variety of protocols. Examples include those protocols that advertise one or more paths per router, maybe QoS metrics, and so on. Third, loop detection should be generic across all the protocols encoded in an IA or an integrated advertisement. So if one protocol is used at one AS to pick paths, another protocol is used at another, the entire set should still be known to avoid loops. Fourth, there should be opportunities to limit the size of these advertisements. You can imagine that an advertisement contains control info for many protocols could be very, very large. So very quickly, here's the current structure we're thinking of, which we think is sufficient to represent. Yeah.
Please quick. Finish up.
So here's the current integrated advertisement structure we're thinking of, which we think is sufficient to represent many of the protocols we analyzed so far. It's BGP-like in that one advertisement is created per destination, but advertisements can be named differently. The data structure includes the following fields. First, one or more paths, which are composed of nodes and edges. Nodes and individual paths can correspond to different granularities of next hops. For example, ASs or, say, border routers. In this case, I'm showing just one path. Second, there can be path, node, and edge descriptors, which state properties of entire paths, nodes, and edges. Right? They can encode things like QoS metrics. We also require node descriptors that contain information about the AS that created that routing node. Right? This is to avoid unwanted hybrid paths. So, right? And the final thing we have here are edge descriptors, which state the AS is used in any of the routing paths contained in the advertisement and is used for loop detection. All right. So just want to quickly conclude with some open questions. First, what are the limits of our proposed modifications? Right? Are there situations where pass-throughs just don't make sense? Second, how does route aggregation affect IA sizes? Right? There might be protocols that just can't be combined, lossily combined, and so you might end up with these advertisements that are really large. And third, how can our modifications be used with protocols that differ in things like the rate at which advertisements can be sent or withdrawn? All right, so that's it. Thank you.